continue with our discussion on noisy channel application to natural language processing. As we have said many times, natural language processing problems are modeled through the noisy channel, and the foundation for this is the argmax based computer. What we have been doing is we are looking at some problems of natural language processing which are amenable to this kind of argmax based computation, and we have chosen 5 representative problems with different characteristics to illustrate these points. And at the heart of all this is the Bayesian decision theory, where we say that amongst multiple choices or options, the one to be chosen will be the one which has the highest probability. And typically the probability is computed as a posterior conditional probability, where B is the conditioning variable and A is the variable of interest. Many of the problems that we will discuss will fall into this kind of framework, and we will see that A and B form conditioned and conditioning pair. Now, we also saw previously that this condition probability is actually many times converted into prior probability P A into likelihood P B given A divided by P B, which is nothing but the Bayes theorem. We have also spent some time discussing why it may be more useful to compute P A given B this way, namely through a prior probability and the likelihood. The question that often arises in the mind of the student is that both probabilities are condition probabilities. So, why should one be preferred over the other? This is the question of generative probability versus discriminative probability, and we will discuss this in detail after some time. So, the question is one of modeling a problem generatively or discriminatively. So, P A given B is the posterior probability, P A is the prior probability, P B given A is the likelihood, and many times this prior probability acts like a filter, providing another parameter for deciding on the best possible option. So, we have been illustrating this point through a number of discussions, through a number of problems. So, we now proceed to take the problems. Before that, the list of problems we have been discussing are part of speech tagging, which will be discussed from the next class in great detail, statistical spell checking, automatic speech recognition, probabilistic parsing, and statistical machine translation. So, these problems are widely diverse problems. So, what is common between these problems, one might wonder, but we see that these problems share one particular idea or one particular consideration, which is that all of these can be probabilistically tackled. So, part of speech tagging requires part of speech labels to be placed on the sentence. Statistical spell checking requires finding the correct word given the wrongly spelt word. Automatic speech recognition is concerned with transcribing speech, that means from the spoken utterances obtain text document, which is machine processable. Then probabilistic parsing is concerned with producing the parse tree of a sentence. Statistical machine translation converts one language into another. So, all of them can be modeled as noisy channel problem and through argmax computation. So, we had spent some time previously on problem number 2, which was spell checking problem, where we had 4 kinds of errors: spelling errors, insertion, substitution, transposition and deletion. We now look at probabilistic speech recognition. The problem here is as defined here. Given a sequence of speech signals, identify the words. We have remarked before that when a person speaks, the hearer correctly recognizes the word boundary. Recognition of the word boundary is a very important problem, and this also leads to a more basic problem, that of isolated word recognition. So, when a word is uttered, how can we decide which word it is, because many times the words sound very similar and the word has to be decided upon from the contextual information. So, this is an important problem. The other problem is of course, the problem of word boundary recognition. In case of word boundary recognition, what happens is that the words are clearly separated and understood as tokens of information as the speech goes on. So, if I say I found a key on the road today. So, this sentence contains a number of words and the hearer isolates the words quite correctly. I found the key on the road today. However, many times this kind of boundary recognition is not an easy task, as seen from the following example, which was discussed when we talked about ambiguity in natural language processing. So, in English, if I say I got a plate very quickly, then there are two possible word boundaries. So, one division could be I got up late today, I woke up late today. Another breaking could be I got a plate today, I got a plate today. So, this is the way the word boundary can be obtained, and this sentence, at least at the spoken level, could be ambiguous with completely two different meanings. Similar is the case in case of the following Hindi utterance, aa jayenge. Aa jayenge can be broken up in two different ways. Aaj aayenge, will come today, or aa jayenge, hum aa jayenge. So, we will come, and therefore, this also is a case of correct word boundary recognition. So, in spoken utterances, this is an important problem. We have also remarked that when we understand speech, we unconsciously keep on producing disfluencies, and we unconsciously process disfluency also. So, many times the speaker takes a bit of time organizing his or her thought, and these are periods of disfluency where meaningless utterances are produced, like I went to the school yesterday, but. So, you notice those points of disfluency where the speaker takes some time producing the sounds ah, etc., and that is used to decide on or organize the next segment of speech which should reach the hearer. So, these problems are basic problems of speech recognition. The problem that we will talk about very briefly is the isolated word recognition. So, the problem definition as was described is, given a sequence of speech signals, identify the words. There are two steps: segmentation, namely word boundary detection, and then identifying the word. We concentrate on isolated word recognition, and this is very well known in the speech community as a basic problem. The problem is to identify the W, the word, given SS, the speech signal. So, this can be formulated as an argmax computation in the following way: W hat is the best possible word given the speech signal, and W is the condition variable here. Best possible in the sense of being the most probable word given this speech signal. So, we compute P w given S s and take an argmax over all possible w which could have come from this speech signal. Okay. So, this becomes an argmax based computation, and the word which has the highest probability is chosen as the answer. Now, one could directly compute these probability from a training corpus. The way the training corpus is created for speech recognition situations is that people's speech are recorded. When somebody produces a dialogue or gives a lecture or speaks over phone, these spoken utterances, sequences of speech signals are recorded. And then what is done is that on these speech utterances, one does the speech engineer does cleaning, then marking the boundaries, and then producing annotations of various kinds. For example, one could annotate the speech signals corresponding to words by their parts of speech. Okay. So, a spoken utterance like I went to the bank, here I is a pronoun, went is a verb, to is a preposition, the is a determiner, and bank is a noun. So, those kind of annotations are produced on the words. Even word boundaries are also some kind of annotation on the spoken utterance record, the recorded speech. We produce this kind of word boundaries, part of speech, emphasis, and so on. Okay. So, this kind of information is important for the machine to process, and this is called annotation. Now, when we produce this kind of annotation, it is possible to train a machine with this speech data, and the parameter which is of interest here, P w given S s, that can be computed from the recorded speech. Okay. So, a very simple approach to this would be, if the speech signal corresponds to that of dog, where you have d sound, ow sound, and g sound, okay, dog, then D-O-G, dog, is the spelling which has to be the output. So, the speech signal is the signal corresponding to the utterance dog with the sound of d, and g, and this produces the output D-O-G. Now, you could imagine that these particular signal corresponding to dog, d, g, these can also be tagged, these can also be processed and output as DAG, or let us say even DEG. Okay. All these possibilities exist. So, what I mean is that I will write it for clarity. What I mean is that the word which corresponds to the speech signal of dog this is the sound content of the word dog. Okay. The sound content of the word dog. So, one could see that depending on how it is produced and the way the speaker produces this sound, it can give rise to SS, is speech signal of dog, can give rise to D, O, G, or D, A, G, or D, E, G, or even things like T, O, G, T, O, K, and so on. Okay. Do you understand this particular point? The point I am making is that it is possible to hear the sound pattern of dog when somebody utters it, it is possible to hear all these strings. So, the sound pattern of dog can correspond to DOG, it can correspond to DAG, dog, if somebody says dog for example, and the output could be A. It could be heard as DEG, confused as DEG, and we know that consonants T and D, they belong to what is called the retroflexive group, retroflexive sounds. Okay. Retroflexive groups T and D belong to this group. So, it is possible to confuse these two sounds T and D, and therefore, the machine could produce TOG. Similarly, there is a group, the Velar group, Velar, which is K and G. Okay. So, K and G also belong to what is called the Velar group or the Kanthya Varna. The sound comes from deep below the throat, and these two can be again confused, and therefore, it is possible for the machine to produce TOG and TOK. Now, you will surely come back and say that all these strings are actually meaningless except for dog, and therefore, this should be the winner. But the point is that it is not a human being who is doing this job of isolated word recognition, but a machine is doing it, a machine which has been trained on people's recorded speech. And we know there is an enormous amount of variation on the way people speak, particularly the vowels, especially the vowels. Vowels have tremendous amount of variation from language to language, speaker to speaker, dialect to dialect. Even the same English language speaker coming from different regions of the world would produce the vowel sounds very differently. Okay. For example, the O sound is very prominent in Bengal, and therefore, it could become dog, okay, where the O sound is extremely prominent, and it is possible to pronounce dog as dog, where the O sound borders on A, and therefore, the machine may be confused to believe that it heard an A sound, and it produces DAG. Okay. So, this is the way a speech signal can be processed and converted into a sequence of characters, and all these are not actually fictitious discussions. These are actual realities. If we speak to the hearers as to what they heard, especially in noisy environment amidst a lot of other speeches going on, okay, a lot of talking going on all around, it is possible for a machine to be confused and produce any of these strings. Okay. The machine may not be robust to all possible noise. Okay. So, one issue is noise, the other issue is the real linguistic problem of confusing consonants when they belong to the same group, and also confusing vowels, because there is an enormous variation in which they are uttered. Okay. Now, comes the role of probability. As you have correctly said that dog should have the highest probability, because this is the string DOG is the string which occurs in the language much more often than strings like DAG, DEG as individual words. And this is the point that is being made. The point is that amongst all these strings which are possible as output from the machine, one of them has the highest probability, and through this argmax computation, okay, catch that string, catch that particular string which has the highest probability, and this probability is computed by means of application of Bayesian theorem and calculating the parameters learned from the corpora. This is the basic idea. So, I hope the point has been properly made, and we proceed with the discussion. So, we have taken this expression of argmax P W given S S over all possible W. W hat is the output string, and this we see has been converted into P W into P S S given W. This is the likelihood, P W is the prior probability over all possible W's. Now, as before we ask the question as to was it necessary to apply Bayesian theorem here. Okay. Could we not work with this probability P W given S S, and let us see how we obtain this probability P W given S S. We obtain this probability from recorded utterances. So, the recorded utterances have been transcribed. I will show you in some kind of imagined situation, but which illustrates the point well. So, this is let us say the speech signal corresponding to dog. Okay, this is the SS dog, the speech signal of dog, and then this corresponds to dog. So, what happens is that we have this signal as shown there, and along with this there is a label which is dog, and the part of speech of this is noun. Okay. So, this is what is done. We have the signal, the label dog, and part of speech noun. There can be many other information plugged onto it, but this is called transcribing and annotating the spoken data. Okay. So, now it should be clear to you as to what should be done with this data. A machine will see these kind of signals, okay, and will also see the label on this. This is dog. Okay. So, I am glossing over some details which will come in a minute. So, just giving you the basic idea as to what is going on. The speech signal and the correspondence dog, this is observed by the machine. Okay. Amongst many other possible signals and their labels, the machine keeps note of the signal it saw and the label it saw alongside. So, it saw the signal, speech signal of dog, it saw the label dog, and increase the count that this signal corresponds to dog. Okay. Now, what should be done is that to compute the probability of dog given this speech signal, okay, we simply count how many times the signal came and how many times was it labeled as dog. Okay. So, we have the signal and the label dog on it. So, how many times did this signal come and how many times was it labeled as dog. Now, the question that might come to your mind is, after all, if I get this signal, isn't it same as dog? What is the point of calculating this probability? This is going to be 1. This is going to be 1, because every time this signal is seen, it is associated with the label dog. Okay. So, that is an important point, and it brings in other things like data sparsity, okay, data sparsity, decoding, which we will discuss as we describe various statistical natural language processing problems. The only thing I could mention to you now is that if the dog is a small string, okay, now if the word is long, for example, procrastination, consider the word procrastination. Okay. So, this is a long word and it will also have a long signal, and it is also possible that this signal as such does not appear in the spoken corpora. Okay. So, what you have is smaller signals, smaller speech signals. Maybe you have a signal corresponding to pro, maybe you have a signal corresponding to shun, okay, and it should be possible to construct the string procrastination from those isolated parts and their probability values. Okay. So, this is the question issue of decoding, and the fact that the signal corresponding to procrastination may not appear in the training corpora. This is the issue of data sparsity. So, it should be possible for us to construct the string from the speech signals of smaller strings. Okay. So, now it should be possible for you to appreciate why the Bayesian theorem application could be a wise step. So, when we apply this process of Bayesian theorem and convert the probability into posterior probability into prior probability into likelihood, what we are doing is that we are taking advantage of a filter in the form of PW. So, PW is the probability of the word, prior probability of the word. So, given the speech signal of dog, we know that it is possible to get dog, dag, talk, tag, so on. However, since dog is a valid word of the language and other strings are not valid, therefore, P dog will be much higher than others, and therefore, it will have a higher chance of winning in terms of probability. The other point, of course, is that this probability seems to be easier to find from recorded corpora, okay, and it is also possible to do this calculation more reliably compared to SS given W, because speech signal, the device that catches the signal is an electronic device subject to error, noise and so on. However, W is a written string of alphabets, and written string of alphabets is likely to be more reliably produced, and the speech signal corresponding to the word may be found more reliably from the recorded data. But I request you to ponder over this question as to which probability is easier to compute and which probability is more reliably found from the corpora, from the recorded speech data. Okay. This is a point you should think about. Now, there are some technical terms well established and well accepted for this probability values. So, P S S given W is the likelihood. This is also called the phonological model, and this we remark here is intuitively more tractable than the probability P W given S S. P W is the prior probability, and it is also called the language model. To be more correct in this particular situation, we should call it the word model. That means, these models the probability or the phenomenon of formation of a word from the constituent alphabets. So, DOG is a valid string in English. DEG is not valid. It is unlikely that this particular string will appear in the corpus. So, PW is computed as number of times W appears in the corpus divided by number of words in the corpus. Proceeding further, how is PSS given W computed? We just gave a very rough idea some time back when we wrote the signal for dog on a piece of paper and the string DOG. Actually, what is done is that a very rich structure, a rich resource called pronunciation dictionary is created and maintained by the automatic speech recognition system. So, this shows a pronunciation automaton for the word tomato. Now, tomato is the string TOMATO, and the word typically is pronounced in two different ways. It could be tomato, okay, or tomato. The A vowel here can be pronounced in two different ways as A or long vowel A or a, okay, which is a combination of two vowel sounds. So, the path corresponding to the pronunciations also are shown here by means of a finite state machine, such that the arcs have probability values. So, now let us follow this finite state machine. T is the first letter, and the machine is in state S1. From T it goes to O with probability 1.0. Imagine here that the whole spoken corpus has only the recording of this particular string, namely tomato. Now, from O it goes to M with probability 1.0. Now, there are two possibilities. One is one could pronounce tomato, in which case this path will be taken. It is a vowel combination of A and E, okay. And in the other case it is the long vowel case A, and from M one could go to M-A or M-A, thus giving rise to tomato, tomato or tomato. Okay. And each path probability can be computed by multiplying the probabilities shown on the arc. We see here that the pronunciation tomato is more likely than the pronunciation tomato, because here we have the probability 0.73, the probability here is 0.27. This simply means that when we recorded the speech of people uttering tomato or tomato, we found that people mostly utter tomato compared to tomato. That is why this probability is higher. So, we will stop this discussion on automatic isolated word recognition, because this is a different topic altogether, which is covered in speech quite extensively. Our goal here is to understand the argmax based computation, and all these descriptions should have been able to convince you that this way of finding the isolated word from the speech signal in the form of an argmax computation is a fairly effective idea, and this particular probability expression P w given S s is converted into likelihood and prior probability. That also is a good idea, because from the pronunciation dictionary we can compute P S s, the likelihood P S s given w, and the prior probability can be computed from a corpora, which is simply the corpus of English language documents. Okay. So, in English language documents we find out how many times does DOG appear, and this occurrence will far outweigh the number of occurrences like let us say TOK or DEG, etc., etc. Those are very unlikely sequences in English language corpora, and we absorb this kind of experience into the probability expression in the form of prior probability. So, I hope this point is clear. We move on to the problem of statistical machine translation, which is an immensely important problem in today's world, where the electronic data on the internet is multilingual in nature. There are multiple languages in the world. The world of web also is no exception. Languages are making their presence felt in the internet by producing their content. And since this is the reality of current day's world, it is conceivable that statistical database techniques, machine learning based techniques, which train a machine from the electronic corpora, can be constructed. So, this is the problem of statistical machine translation. By the way, statistical approach to machine translation is relatively new. Translating from one language to another language has been an extremely important problem, very old problem. In fact, the whole field of natural language processing is said to have started when in the Cold War days, there was this important requirement of translating from English to Russian and Russian to English, and there was quite an amount of money spent on this particular problem. And there the approach was to look up dictionaries and then create intricate rules for transforming structures from one language to another, and this approach of course has remained and produced very successful systems like Systran, which is an effective system for translating between European languages and English. Now, the statistical machine translation approach became popular in last, let us say, about 10 to 15 years, where lot of electronic data in different languages became available. And an important resource which is needed in statistical machine translation is what is called Parallelcorpora. Let me give you an example to make your understanding clear on this point. So, Parallelcorpora, just I will take 2 minutes to annotate the slides. Okay. So, Parallelcorpora means sentences in two different languages which are translations of each other. So, you essentially create a very large resource base of sentences in two different languages, the source language and the target language, between which the translation is required, and these are kept aligned with one another, and that is why it is called a Parallelcorpora. To give an example, suppose you say that Mumbai is a big city and the corresponding Hindi translation is Mumbai एक बड़ा शहर है. Okay. The city is very busy. This is another sentence. The city is very busy. The corresponding translation is यह शहर बहुत व्यस्त है. Okay. So, this is an example of Parallelcorpora, of course, an extremely small corpora, where we have English sentences and the corresponding Hindi sentences. Mumbai is a big city. Mumbai एक बड़ा शहर है. The city is very busy. यह शहर बहुत व्यस्त है. Now, when this kind of sentences have been aligned, okay, they have been placed in correspondence to each other, we obtain what is called the Parallelcorpora. And the key idea here is that a machine is shown this kind of parallel translations, and it is trained from these parallel translations, the translation patterns and the units. So, the machine learns that MUMBAI in English corresponds to Mumbai in Devanagari in Hindi. Okay. A city corresponds to Shahar, okay. Is corresponds to hai, a corresponds to ek, and big corresponds to bada. So, you can see that the English in English for this particular sentence there are 5 words. Mumbai is a big city. Hindi also has 5 words. Mumbai ek bada shahar hai, but the word order has changed. Okay. The word city was the last word in the English sentence, whereas this is the second last word in the Hindi sentence. Also, see the movement of the verb is. It is an auxiliary verb, and from being the second word in the source sentence, it has become the last word in the target sentence. Okay. So, this way words change their position. Many times words get dropped in the translation, or they get conflated. That means, a particular word can give rise to more than one word. Okay. So, this is the problem of learning the patterns when the sentences are placed in close correspondence. So, the city is very busy. This is a 5 word sentence. Yah shahar bahut vyast hai. This also is a 5 word sentence, and one can establish one to one correspondence, albeit with the recognition of the fact that the words can occupy different positions in the source sentence and the target language sentence. So, the machine creates a mapping of words or double words or triple words, technically called unigram, bigram, trigram, established correspondences, and these correspondences are then used on a new sentence to produce the new target language output. Okay. So, here again you can see there is a process of breaking apart the units, learning their correspondences and using them conveniently when a new sentence is given. This is the basic idea, and it can again be formulated as a noisy channel and argmax based computation. So, the question being asked is, what sentence in the target language will maximize the probability P target sentence given the source sentence. Okay. The picture shows the situation, source language sentence goes through the noisy channel and becomes the target language sentence. This is a metaphor which is found convenient. Now, we have discussed to an extent the importance of parallel texts, where the translatable units, translation units and their mappings are learned. Where does one get the parallel text from? Typically, the sources are instruction manuals. For English Chinese translation, which is an important problem in today's world for many commercial reasons, the Hong Kong legislation documents are used, because these documents are available in 2 languages, in English and Chinese. Macau legislation is again similarly for translation between English and another language. Canadian Parliament Hansard's is the Parallelcorpora used for English to French machine translation, which by the way is of very high quality. United Nations reports are available in 6 official languages of UN, namely English, French, Spanish, Chinese, Arabic. United Nations reports are available in these languages, they form Parallelcorpora. Similarly, there is something called Parallelcorpora, which is not mentioned here, very famous. Parallelcorpora is available in languages of Europe, and they are in very good sentence aligned form, and they can be used for training a machine. In India, documents are typically available in 3 languages, because every state implements the 3 language formula: English, Hindi and the language of the state, and therefore, that is a good source of Parallelcorpora. The statistical machine translation formalism would be as follows: source language is called F, target language is E, source language sentences are small f, target language sentences are small e, source language word is W upper suffix f, target language word is W upper suffix e. Then to translate f, we assume that all sentences in E are translations of f with some probability. Okay. So, that is the interesting position, because we have the scoring function in terms of probability anyway, and therefore, we can assume that every sentence in E are candidates for translation of small f. And finally, we choose the translation with the highest probability, which immediately makes the situation amenable to an argmax based computation, where E hat is equal to argmax over E of the expression P E given f. Okay. So, f is the source sentence, E is the target sentence. Now, we apply Bayes theorem here, and the reason for applying Bayes theorem is quite clear in this particular case, because we want to make use of the prior probability P E. P is called the language model, more appropriately possibly should be called the sentence model, because E is a sentence and the value of E or the probability of E goes up if it is a valid sentence of the language, because this occurs much more frequently in the corpora than ungrammatical wrong sentences. P f given E is the modeling of the translation efficacy from E to f. This is called the translation model, and this stands for faithfulness, which means how much of the content of E is transferred to f. Okay. The better the meaning correspondence, higher will be this probability, and P E is the modeling of the fluency situation. Okay. If a sentence is fluent in the language, grammatically correct, idiomatically correct, P E value will go up, and f, if f has strong translation correspondence with E, then this value will go up, and therefore, E f is very faithful to E, f is a faithful rendering of E. So, both these are computed by breaking them down into smaller components of what are called n-grams. N-grams are language models, which will be a topic of discussion for us later. Now, we come to a very important problem of natural language processing, a fundamental problem of natural language processing called parsing. Those of you who have done a course in compilers would know what parsing is. A fragment of program, okay, a C program, Fortran program passes through the parsing stage for correctness in structure, and this parsing produces what is called the parse tree. Here also we can think of the problem as a problem of passing the source sentence through a noisy channel and obtaining the target parse through an argmax based computation. This argmax based computation is expressed through these equations here. T star is the target parse, and this is obtained by argmaxing over T for the probability values of P t given S. So, S is the sentence, T is the tree. So, P t given S is the conditioned probability, and for different values of T, it has different values. So, choose that T which has the best possible probability, best probability. Now, in this case again we apply Bayes theorem and we convert it into P t, the prior probability, into P s given T, the likelihood. Now, here the application of Bayes theorem is eminently suitable for a very interesting fact. P s given T, what is this? This is the probability of the sentence S given the tree T. Now, one could see that if the tree is known, then there is no reason to have any uncertainty about the sentence, because one simply stitches together the words at the leaf level and produces the sentence. So, P as given T is 1, therefore, T star equal to arg max P T. So, choose that particular tree, parse tree which has the highest probability. We discuss this, continue this discussion in the next lecture.